Good morning, ladies and gentlemen. I really dressed up for all of you today as you guys are at home staying warm. So, all right. I'm going to go through the part one for Taylor and Maclaurin polynomials or series. Okay, so first of all, I want a little review question here. Is I gave you blah of x, I made one up, and it converges from -1 to 1. We're going to find the following series and the associated interval of convergence. So blah of 2 of x, I'm just going to, wherever I see x, I'm going to replace it with 2x. And if you look, my center is still at 0. Okay, but I also want to go find what our interval of convergence is. So I'm going to put 2x between -1 and 1, because this is modeled after it's a geometric. So if I divide by 2, my interval of convergence is between -1/2 and 1/2. Okay? By the way, the joke here, it's blah, blah, blah. Anyway. All right, so I want to find blah of 3x minus 5. So I'm going to go substitute in 3x minus 5 wherever I see x in the original one. So there is my general term. And my center here, if you think about it, is going to be 5/3. Okay? Because I'm just trying to find where this is 0. All right, so my interval is from -1 is less than 3x minus 5 is less than 1. So if I add 5 to there, I get 4 is less than 3x is less than 6. If I divide by 3, I get 4/3 is less than x is less than 2. So that's my interval of convergence, and if you look, 5/3 is right in the middle of those two, because that's really 6/3. All right. So now, we also now want to go find the derivative of blah of x. So that just means I'm going to go differentiate term by term. And if you remember, my interval does not change. So if I differentiate term by term, I get 1 plus 8x plus 27x squared plus 64, 64x cubed plus ... plus my general term is then going to be, it's still n squared, because remember I'm differentiating with respect to x, not n, and it's going to be times n to the x, or x to the n minus 1, which really is n cubed times x to the n minus 1. Okay? So if I now look at that, remember, since I differentiated, my interval doesn't change. Well, look, this is r still. So r would still be between -1 and 1. All right, so the last one is I'm going to integrate it, but you notice I have to write it as a t, and then it'll integrate between 0 and x. So I'm first going to integrate t plus 4t squared plus 9t cubed plus ... I want to do at least 3 terms, n squared t to the n dt from 0 to x. So if I integrate the first term, I know I get 1/2 t squared, 1/2 t squared. The next one, I'm going to get 4/3 t cubed. The next one, I'm going to get 9/4 t to the 4th plus, and then I know I'm going to have an n squared on top. It's going to be t to the n plus 1. But now I'm going to have n plus 1 on the bottom. And that's my general term. But I need to go now evaluate between 0 and x. Well, the nice thing is when I plug in 0, I'm not going to get anything on any of those terms. So we get 1/2 x squared plus 4/3 x cubed plus 9/4 x to the 4th plus, and my general term would be n over n plus 1 times x to the n plus 1. Okay? And if you think about it, my center on blah was between 0 and 1, and because this is theorem 1 that this held true, theorem 2 holds true that when you integrate a function, its interval does not change, so its interval is still from -1 to 1. Okay? All right. Now, all we're going to do on these is to differentiate with respect to x. So just a little practice on differentiating a general term. All right, remember, we're not going to touch the n's here. We're just going to, we're not going to differentiate 5 to the n or n factorial because we're differentiating with respect to x. Okay, So dy dx, or y prime, however you choose to write it, is going to be 5 to the n times x minus c, there's going to be an n in front, to the n minus 1, and then when I differentiate this x inside there, I just get a 1 all over n factorial. Okay? But we do have some simplifying we could do, because you remember I have an n here, and n factorial is n times n minus 1 times n minus 2 times n minus 3 all the way until you get to 1. So an n is going to cancel out of both of those. So what's left on the bottom, when I get rid of that, is n minus 1 factorial. So this becomes 5 to the n, and then it's x minus c to the n minus 1 over n minus 1 factorial. Okay? Now you notice, if the powers matched here, if the power and the factorial match here, the power and the factorial match there. Okay, so the same will probably come true here. So dy dx for number 2, remember, this just comes along for the ride. There's no x in it, so it's going to be negative 1 to the n. Now when I differentiate this, I get n plus 1 times x to the n all over n plus 1 factorial, which, by the way, you know after that is n, and it's just got one more term on it than this one. So an n plus 1 cancels out, and I'm left with negative 1 to the n, x to the n, and when I cancel out an n plus 1, it's just n factorial. Okay? All right, our last one is number 3, and that's going to be dy dx again, is equal to, when I differentiate this, it's going to be 2n plus 3 times x minus a to the 2n plus 2. I just lowered it by 1. Okay, all over 2n plus 3 factorial, which, by the way, is really 2n plus 3 times 2n plus 2 factorial, if it's easier for you to see it that way. I could have written this as, over here, n times n minus 1 n plus 1 times n factorial, and you realize it's a little bit easier to cancel then. Okay, derivative of this is still 1, so really when I simplify that, it's going to be x minus a to the 2n plus 2 all over 2n plus 2 factorial once I cancel those. Okay, so now we're going to do the nth derivative of each of these. I'm going to save the third one or the last one until we come into class. So we're just going to find each derivative. We're going to find a bunch of derivatives. So this is going to be 5 to the first. I'm going to write it that way because you'll see it a little bit quicker. The second derivative, when I differentiate this again, remember that's a constant, so it's 5 squared e to the 5x. Y triple prime is 5 cubed times e to the 5x. Well, what's happening is the exponent on the 5 is the same as the derivative. So what will the nth derivative be? It's going to be 5 to the n e to the 5x. Okay? And you may say, well, why are we going to use this? Well, very simple, because of the fact that when we are doing what's called a Taylor series, we're going to have to take many derivatives, and being able to generalize what the nth derivative will be will make our lives a little bit easier. Okay, number 2 should really be 5 to the x. Okay, not 5 to the n, because if you differentiate with respect to x, we wouldn't have a derivative. All right, so y prime is, remember that's still exponential, is going to be 5 to the x. When I differentiate, I get a natural log of 5. Okay, when I do the second derivative, it's going to be 5 to the x, but now I'm actually going to get 2 natural log of 5s, or I can just write it as a quantity squared. Now, I want to point out that 2 does not come out in front because it's not 5 squared, it's the natural log of 5 is squared. Okay, the third derivative is it's still going to be 5 to the x, and I'm going to get another natural log of 5. Okay, so really, what is our general term? Well, if you notice, the derivative number and the exponent of the natural log of 5 are the same. So the nth power would be the natural log of 5 to the n times 5 to the x. Okay? All right, so the third one is a little trickier to see. All right, so y prime, and we've talked about this, is negative 1 over x squared. Okay? All right, y triple prime, or y double prime, is you're going to get x to the fourth on the bottom, and then it's low d high, which is 0, minus high, so it becomes plus, times drew to the bottom, which is 2x. So I really get 2 over x cubed. Okay? All right, the third derivative is going to be, well, I get an x to the sixth on the bottom when I double it, and then it's low d high, which is 0 minus high, times the derivative of the bottom, which is 3x squared. If I simplify it, I get negative 6 over x to the fourth. Okay, if you look, the power in the denominator is getting bigger, and the numerator is alternating, and its sign is alternating, and there's a pattern that's developing. So we'll do one more derivative. We'll do the fourth derivative, and it's going to be x to the eighth on the bottom, and then it's low d high minus high d low, so it's minus high will make it positive 6 times 4x cubed, which is 24 over x to the fifth. Well, if you look at this, y to the n, all right, what's the relationship between the exponent and the power on the bottom is 1 bigger. So if this is to the n, this is n plus 1. And whenever it's odd, it's negative. So I write that as negative 1 to the n, as we've talked about before. And now if you look at the numerator, that is a what? It's a factorial. Well, that's 1 factorial, that is 2 factorial, that's 3, and that's 4. So what's it going to be up top? N factorial. Okay? All right. So that is our first page. I'm going to clip this one at this point. Stop this video. The next pages go a little bit quicker, but I wanted to go through that one in pretty close detail. Thank you, guys.